Good morning, everyone. Thanks for joining. I'm very excited to welcome you to the first ever Wolfram Philippines User Conference. My name is Yuli, and I'll be your host today. First of all, I would like to thank our speakers who will be sharing how they use Wolfram in their projects. And I would also like to thank Dr. Nick, Aaron, and Philippine Consortium team for all of your support to facilitate this event. We have got excellent speakers today, as seen in the agenda. Our speakers have kindly recorded their talk in case of connectivity issues, but they're also here to answer any questions. Feel free to post your questions in the Q&A chat on the right-hand side of your screen. To keep the chat organized, we'll only publish messages that are helpful to the whole group. You can also check if your organization also already have a Wolfram access through the link here. At the end of the session, you'll be prompted to complete a survey. You can also select to receive a certificate of attendance. If you would like to receive this will be sent directly to your email. I will then now pass to Philippine Consortium team for a quick introduction. Oh, hi, Dr. Nick. How are you?
Hi, I'm good. Yuli, how are you? Let's
I'm good,
start.
thanks.
Yeah,
Would you like to do a quick introductions about Philippine Consortium team? So Philippine Consortium is a Wolfram sole local partner in the Philippines.
yes. So the Philippine Consortium is the sole distributor and partner of Wolfram Mathematica in the Philippines. I would like to acknowledge and give thanks to Wolfram Mathematica for this opportunity and for the Philippine Junior Data Science Society. I would like to give thanks and acknowledge the University of the Philippines Junior Data Science Society as our partner and all the data scientists. So right now, one of our mission is to make Wolfram Mathematica accessible to every students and every researchers, not only for UP, Ateneo, La Salle, and UST or the Big Four. So secondly is we still have corporate social responsibility. So we provide sponsorship support to academic conferences. Just send us an email and we provide free trainings and conferences for our Wolfram Mathematica users. Please visit our website www.philconsortium.com and you could download all the brochures, look at the video tutorials, and you could see our list of products, AI tools, and services. Again, we want Wolfram Mathematica to be accessible to every student, researchers, academic faculty, because that will give us the equal opportunity to learn and to use this most advanced tech computing software and AI tool. And it's Wolfram Mathematica basically is used by the industry. So just send us an email, marketing at philconsortium.com. And happy Wolframing, everyone. And have a great Wolfram Philippines User Conference 2025. So it's historically it's the first one, and we will have it every year. God bless everyone. Happy Wolframing.
Thank you so much, Dr. Nick. So next, I would like to introduce you to Dr. Professor Luis Antoinette de la Peña, who will be presenting and opening for today's event. Thank you so much, Robs. I think in that case, we can come back to Professor de la Peña's, but I would like to introduce you to our very first speaker of the day, Dr. Mark D. Tomanes, who is from Ateneo de Manila University and will be sharing with us his project with Wolfram Mathematica on exploration and constructions of tilings.
Good morning, everyone. I'm Mark K. Tomenes from the Ateneo de Manila University. First of all, I would like to thank Wolfram and the Philippine Consortium Inc. in inviting me in this event to present to you and to discuss how we do an exploration and construction of tilings through Mathematica. Before we begin the actual exploration and construction of tilings in Mathematica, first, let's begin with some definition and concepts so that we can fully understand what's happening when we are constructing tilings. First, we define what a tiling is. It is just a countable family of closed sets which cover the plane without gaps or overlaps. So essentially, you can think of your usual floor tiling, wherein we have what we call the tiles. So these tiles that you can see in the floor tiling, it covers the plane, the whole floor without gaps, and there are also no overlaps. So that is what tiling is intuitively. Now, the intersection of two or more of these tiles can be an isolated point or an arc. The points, those are what we call the vertices, and the arcs, those are what we call the edges. Now, there's a lot of application of tilings. It's not only theoretical, but you can find this in a lot of objects. For example, the artworks by MC Escher can be considered as tilings. You can consider those shapes as your tiles. This, for instance, these fishes here and boats can be considered as tiles, and they cover the planes. There's no gaps and there are no overlaps. You can also see uh, tilings and patterns as well in the works of our indigenous people. In architecture, tilings are also present, as well as uh, the designs that you can see in the Alhambra Palace in Spain. You can also see tilings in nature and also in chemistry. Tilings are present. Now, what we have been doing in the previous years, in fact, subject of my dissertation and also my postdoctoral studies, is what we call an ABC tiling. So, what is an ABC tiling? Basically, you have a tiling and it consists of vertices, edges, and tiles. Now, if we were able to identify the number of types of vertices, edges, and tiles, say there are A types of orbit of vertices, B types of edges, and C number of types of tiles, we call that tiling an ABC tiling. So, so yeah, that's what an ABC tiling is. Now, what's interesting is the three-dimensional analog of these ABC tilings. Because as it turns out, ABC tilings are, especially for small values of A, B, and C, can be used in design synthesis. While my expertise, while my expertise is on the mathematical side, these structures resemble those used in crystallography and material design. So this makes ABC tilings a promising bridge for collaboration between mathematicians and crystallographers and chemists. So in fact, just recently, the Nobel Prize in Chemistry was just awarded to these um, three scientists, Suzumu Kitagawa, Richard Robson, and Omar Yagi. So uh, they were awarded the Nobel Prize for the development of metal organic frameworks. And as I've said, these ABC tilings can kind of be used to model these metal organic frameworks. Now, before we begin to understand and construct tilings, we have to learn what symmetries are, because symmetries are going to be the tools we need to construct tilings. So let's try to understand what symmetry is. The symmetry of an object in the plane is an isometry that sends the object to itself. Basically, you have this operation, which we call symmetry, such that when you apply this particular operation on an object, the object should go back to itself. There are four types of symmetries, and I think you're quite familiar with these symmetries. First is a rotation. Okay? So a rotation is defined by an angle and a center. For example, let's consider this logo of Mathematica. Okay, this logo has what we call a five-fold rotation with this particular center. A five-fold rotation is just a 72 degrees rotation. So when you rotate this particular logo on this center, what you will see is that the object will just go back to itself. So that's what we mean by asymmetry. When you perform the symmetry, the object will just go back to itself. Of course, that's not the only rotational symmetry that this object could have. You could also have 72 degrees, 144 degrees, 216 degrees, basically multiples of 72 degrees. So that is the first one. The next symmetry is what we call a reflection. You can think it is defined by an axis represented by a line. And you can think of a reflection like a mirror. You know, what you see on one side of the reflection line should be exactly what you will see on the other side. So when you perform the reflection, the logo will be sent to itself since the halves are exactly the same. Now, this logo does not only have this reflectional symmetry, it also have other reflectional symmetry, like all of this reflection. Okay. Now, in connection with symmetries in mathematics, there is what we call a symmetry group. Basically, if you collect all of the symmetries of an object, collect them in a set, that set is what we call a symmetry group. So for example, this particular logo, we'll learn that it contains rotational symmetries, it contains reflectional symmetries. Collect all of them, that is the symmetry group of this particular. Okay, now for finite object like this one, there are you can have two types of symmetry groups, which we call cyclic and dihedral groups. Cyclic groups are only purely rotational symmetries, so it does not contain reflections, while dihedral groups contains rotations and reflections. So that's the difference. Okay. Now, for instance, this particular logo here, its symmetry group is what we call D5 or dihedral group. Dihedral group of order 10. So it is denoted by D5. That means that it contains five-fold rotational symmetries, or that's 72-degree rotation, and also five reflectional symmetries. Okay, that's it for finite. Now let's move on for infinite objects. Like for example, the tiling that I presented earlier. That's an infinite object. Aside from rotation and reflections, um, it turns out that infinite objects can also have what we call a translational symmetries. So, for instance, this particular tiling, it has a translational um, symmetry. So what does translation symmetry means? It just means that you are shifting the tiling so that it's going to itself. So a translation is defined by a vector, and a vector is defined by a distance and a direction. The direction is telling you where to shift, and the distance is telling you by how much distance are you going to shift. Okay, so that is translation. Now, the last type of symmetry is what we call a glide reflection. A glide reflection um, is just a combination of two symmetries. It's a combination of translation and a reflection. So, for example, if it's a combination of translation and reflection, you must have a vector and an axis. So, for example, here, you translate first and then you reflect. So it is a combination of those two types. And as you can see from this diagram, after you do the translation and then reflection, the tiling will just go back to itself. So that those are the symmetries. Now, I mentioned earlier that for finite objects, there are only two types of symmetry groups. Either you have CN, cyclic group, or DN, dihedral groups. As it turns out, for infinite objects like tilings and patterns, you could have 17 different types of symmetry groups. We call them plane crystallographic groups. And they are depicted by one of these diagrams, which we call lattice units. Okay, so they belong to one of these. So let's take, for example, this group, which we call P4M. This diagram just denotes the symmetries present in this particular group. These blue lines, blue solid lines here, that you can see that those are the axis of reflections. You know that already, the reflections. We also have rotations here. Um, those red squares, they are centers of rotation, a 90-degree rotation. All the circles are centers of rotation as well, but they are 180-degree rotation. We also have a dotted line here. That dotted line is an axis of glide reflection, while the black line here is a vector, which defines your translation. Now, there's a lot of things there's a lot of information that we can gather from this particular diagram. By the way, this diagram is what we call a lattice unit. A lattice unit is the minimal region that, when translated by two independent directions, fills the whole plane without gaps or overlaps, essentially creating a pattern or a tiling. So, for example, if you have a pattern and then you put your pattern inside this lattice unit and then use the vectors in order to translate that particular pattern, then you will generate an infinite pattern. I will show this to you later. Now, aside from lattice unit, there's also what we call a fundamental region. It's the smallest piece of a pattern that generates the entire design when all symmetries of the pattern are applied to it, including reflection, rotations, and glide reflections. The fundamental region is this darker pink region here inside the lattice unit. So the difference between a lattice unit and a fundamental region is that the lattice unit only considers the translations that you're going to apply to that lattice unit, while the fundamental region, you are going to apply all of the symmetries. So for example, from this fundamental region here, so basically what you can do is to reflect it or rotate it so that you can fill the entire lattice unit. So now that you have the lattice unit, you can translate it using the vectors so you can generate the whole tile. Here is an example of what I was talking about. So here I superimposed a pattern and that lattice unit P4M. So for example, you have this small pink region here, the darker pink region. If you try to reflect and rotate, you will get a pattern inside the lattice unit, and then when you apply translation, you will get the entire symmetry. Okay, I created an animation so that you can see what's happening here. This is essentially what we are going to implement in Mathematica later. Essentially, once you are given a fundamental region, you should be able to generate the entirety of the tiling. Because what you can do is just to use all the symmetries in order to propagate the fundamental region to infinity. That means that whenever you have information about the fundamental region, you can use those information in order to generate the whole infinity of the tile. So here, what I just did is from the fundamental region, I reflected it, doing some rotation. Now that's your lattice unit. You translate them to generate the entirety of the pattern. By the way, the pattern is infinite. Of course, I cannot show an infinite tiling here. So I'm just showing you a patch of that particular. Okay. So this is what we are going to implement later in Mathematica, how to create this kind of tiling. Okay, now let's go back a bit from our definition of the ABC tiling that I was talking about earlier. So I've said we are trying to create this kind of tilings. So meaning if I was given values of A, B, and C, is there a way on how to create that tiling with that particular properties that it has A kinds of vertices, B kinds of edges, and C kinds of tiles? As it turns out, there is a way. And we obtain this particular theorem that allows us to construct these kinds of tilings. Of course, I'm not going to prove this to you, but I just wanted to show you how we do the construction. So we start with some known tiling. It has what we call a symmetry group, and it has a subgroup. A subgroup is just a subset of that particular group. So what we did is to get a subgroup. Um, the subgroup has its own fundamental region. In this figure, you can see this triangle bounded by this line. This is the fundamental region of this particular subgroup. So just as what I've told you earlier, once you have information about the fundamental region, you can generally obtain the entirety of the tiling. Okay, so once you obtain that fundamental region, we construct the vertices in the fundamental region and then apply the symmetries in order to get all of the vertices. Then we constructed the edges inside the fundamental region and again apply the symmetries in order to generate the entirety of the tiling. So that's it. That's how we construct tilings. Now, um, how are we going to uh, do this? There are different softwares that we did use in order to construct the tilings. So we can use GeoGebra and Wolfram to visualize the tilings. We also use GAP, groups, algorithms, and programming for computation of subgroups. So these are things that we can use in constructing and computing tilings. So let's try to implement this in Mathematica. So the things that we need are a fundamental region and and the lattice unit of the symmetry group that you wanted to create. For example, if you wanted to create a tiling having a symmetry group that is PMM, that has I showed you the lattice units earlier of different symmetry groups. This is the lattice unit for PMM. So it has reflections, it has rotations, it also has these translations. And now, if you wanted to create a tiling with this particular fundamental region, by the way, I just created this using GeoGebra. So in GeoGebra, you can kind of construct points and arcs. It's easier because you can just simply plot the points, connect the points. So it's easier in that way. And then I just color coded them. And then, as I've told you, you just have to put that particular fundamental region inside that pink region that I showed you earlier, and then use the symmetries in order to create the whole tiling. So that's what we are going to implement in Mathematica. So here's the code that I generated. Essentially, the first one is defining the fundamental region. Now, later on, what we are going to do is to use symmetries in order to propagate this fundamental region in the infinite plane. So the first thing that I need to do is to fix the location of that particular fundamental region, and that's going to be important because we will be doing reflection along an axis. So for instance, this axis, these are lines, so they have their corresponding equations. So for example, we can say that we reflect on this particular line, a vertical line. So it has its own equation. So we can tell Mathematica to reflect along this line, and then I'm going to give the equation of that line. So it's important to fix them in a particular region. So I fix them at this bottom left of this fundamental region. Okay. So yeah, the next few codes here is essentially implementing the symmetries of in the fundamental region. So for example, here you are reflecting along that axis. So, and by the way, in this code, you will see here some numbers. As it turns out, symmetries, these are operations that can also be represented by matrices. So this represents a matrix and some translation vector. So that's it. And then here I also have another reflection. So it reflects this fundamental region going to that other fundamental region. Then I also did a twofold rotation or a 180-degree rotation, sending this fundamental region to the other one. So I did those three transformation or symmetries, which when you try to paste together will give you this particular lattice unit. So now that you have a lattice unit, I hope you still remember that what you do next is to just simply translate, because that's how we defined lattice unit earlier. It is the smallest region that when you translate, you can get the whole tile. So in Mathematica, there's a way on how you can translate. I think there's a code, but what I did is to use the table command. So what I did is to actually I know that when I have a lattice unit, I can just simply repeat it again and again into directions. So for example, here I created a table, and then in each cell of that table, I put my lattice unit. So this is what it will look like. So I created this table and put, because I'll just be repeating my lattice unit. And then I use this code image assemble in order to paste together all of these lattice units. And I will be able to create a 2-3-2 tiling. By the way, I'm not claiming that this is the most efficient way on how you can uh, code or implement the theoretical framework that I presented earlier. But I think there's a lot of you guys that's more uh, creative than I am in doing these codes. Yeah, uh, creativity also plays an important part here. Okay, now what's good about this one is now now that you have this particular code, you can just simply replace your fundamental region by any fundamental region that you want. So for example, I replace it by this particular configuration of vertices and edges, then I will be able to create this different tiling here, which is a 3-3-2 tiling. It has three types of vertices, three types of edges, and two types of tiles. So that's good, right? Because now you can just simply change your fundamental region in order to create a different tiling. Meaning you can now do your investigation much faster, because you can create a lot of examples, consider those examples, and then do observations, make conjectures. You can do a lot of things here. Now, this is not only limited to tilings, but also in patterns in general. For example, here, I was able to create this kind of pattern by using as a fundamental region a motif found in the products of our indigenous people here in the Philippines, in particular the Pinalian by Tingians. So I was able to create this pattern. Now, um, I'm not claiming that I'm not really very expert in everything about Mathematica. In fact, all of these codes, um, I I'm not very familiar with all of the built-in codes in Mathematica. But what's good is this um, what's good about Mathematica is this particular tool. So Mathematica has a built-in built-in AI that we can use here. So apparently, I know a lot of you guys have already known that you can use natural language in order to communicate with AI, and Mathematica has its own built-in AI. So meaning you don't really need to know the code in order to implement what you have in mind. So for example, you can actually use natural language in order to let Mathematica know what you want to do. So for example, here, I want to create a tiling with symmetry group PMM. Of course, I'm not expecting Mathematica to know what that PMM means. So I just give some additional instructions what to do. And yeah, I'm just using natural language to describe what I want to implement. And Mathematica can translate that into codes that you can use to communicate with Mathematica so that it can compute what you want to do. So it gives me this code, and then I can um, insert and evaluate, copy the code. Of course, there are times that it might fail. So probably you might think about your prompts and then try to edit it. So you can, a lot of the time, you have to edit your prompt so that Mathematica and you could understand each other. So I tried to create another prompt that is, you know, kind of more specific. So I did this prompt. So Mathematica is teaching me how to do it. It's telling me what codes to use. And yeah, so I tried to use the code created by this AI. And as it turns out, it did quite well. So probably you will be doing this, editing the prompt in a lot of iterations, but yeah, you just keep on editing your prompt in order to generate exactly the thing that you wanted to do. In fact, you can also edit this manually if you think that there are things that that the AI failed to do. So you can edit this manually. You can even change your fundamental region here, and then it was able to create the tiling that I want. So I think I already exceeded my time, and uh, this is I have to stop here, and I hope that you learned something in this session, and thank you for listening.
Thank you very much, Dr. Mark, for sharing about your project. So, if you have any questions for Dr. Mark, you can put them on the chat window. He might come back to you to answer them. But in the meantime, I would like to introduce Professor Luis Antoinette de la Peña, who will be sharing a bit of opening remarks. Hopefully, she's able now to use her microphone. Um, Hello, Professor de la Peña. How are you?
Hello, good morning. Can you hear me?
Yes, we can hear you.
Okay, so that's good. Apologies for the earlier mishap on my uh, gadget. And thank you very much. So, good morning to everyone tuned in today's webinar. So, good morning, Dr. Nicamil Sanchez, Chief Executive Officer of Philippine Consortium Inc., mathematicians, data scientists, computer scientists, engineers, our students, researchers, colleagues, all joining us today, ladies and gentlemen. Um, I am here today speaking on behalf of the National Research Council of the Philippines, for which I am the current president. And it is indeed an honor for me to welcome all of you today at the 2025 Wolfram Philippines User Conference. I am pleased that this conference brings together our friends from Wolfram, as well as colleagues and professionals in the Philippines and in other areas in the world to speak and discuss meaningful ideas. So during this day's age of AI, where a lot of technological tools are available for us to use in the academe and industry, it is important that we are guided on how technologies can be used and optimized for our work in our teaching, whether how we use it in the corporate setting and research. Thus, I am grateful that Wolfram Philippine Consortium Inc. has been generous in organizing this event to inform the community of the new tools that are available. I am very much aware of Wolfram technology. I am a user of Mathematica for the past 20 years. I'd like to share one of my papers about 13 to 15 years ago was on the CAS capability of Mathematica. I presented a work on designing color models for my teaching in abstract algebra. And this was in 2001. There was a conference on modeling, simulation, and scientific computing, some in Mindanao, and a number of us from the Ateneo de Manila University talked about Mathematica during this workshop. And also, sometime in 2012, I remember talking about more of these color models as tools in teaching mathematics in the 17th or the 7th Asian Technology Conference in Mathematics, quite some time ago. And today, Wolfram technology has gone a long way. The power of Wolfram has multiplied, or probably even up to a certain degree of exponentiation. And it has allowed us to explore to the fullest not just estimation and numerical computations, strengthening algebraic and symbolic solutions, carrying out advanced problem solving, arriving at innovative approaches and well informed decisions in the process. And also, I'd like to mention the power of Wolfram to facilitate multidisciplinary approaches in solving problems and carrying out research. So, at the National Research Council of the Philippines, we are focusing on multidisciplinary approaches. Our problems cannot anymore require a traditional approach. We need to bring minds from different disciplines together. And I think this is one of the best features of Mathematica and Wolfram technology. In the last Mathematical Society of the Philippines convention, I talked about the benefits and challenges of AI in mathematics education. Among the benefits is personalized instruction. We need individual needs of students to be addressed at this age and time, where there are a lot of issues, not just on academic survival, but on mental health as well. AI's benefit is also providing the interactive learning environment, such as gamification, engaging students through an active learning environment, promoting active participation, problem solving, and critical thinking. And of course, there is the benefit of real time feedback. Earlier, you've seen Dr. Tomenes create codes, and immediate feedback on whatever it is that you want to attain is given. And this is very important in assisting students in providing solutions and correcting errors, pointing them to the right direction towards correct answers, reinforcing learning, and developing problem solving skills. And I know that Mathematica incorporates a variety of AI technologies that are very useful, powered by machine learning, symbolic computation, and LLMs, or what we call the large language models. And I'm very, very happy about the Wolfram Notebook Assistant. One can enter some problems in his or her own words. And what is important is communicating back to a precise computational language the answer, which is reliable and consistent and could help teachers, students, and researchers. So for today and probably even in the next months or years, let us use these kinds of forum, such as what we have today, as a working space for learning and discovery, opportunity to assess what we are doing in terms of technology, how we can refine the use of technology, and acting with the use of new technologies to improve how we teach our students, carry out research. But I'd also like a gentle reminder that we do this within the bounds of research ethics. So I'd really like to thank everyone involved in this webinar, the speakers, the efforts of Philippine Consortium alongside Wolfram for making this happen to millions of people in the academe industry around the world. So thank you very much, and I look forward to more interactions and more dealings. And perhaps one of these days, you could also have a webinar for the National Research Council of the Philippines. And we would be very, very happy to facilitate this for you. So thank you very much. Maraming salamat and have a pleasant day ahead.
Thank you very much, Professor De La Peñas, for your opening remarks. Certainly, we are very. It's a pleasure to help you to have you here. It's an honor to have you at this event. Wolfram would be very keen to have another webinar for National Research Council of the Philippines as well.
Okay, anything we could do to help your cause, that's really a pleasure on our part. So thank you so much and have a good morning.
Thank you. Continuing on our event for today, earlier you saw an example of a notebook assistance by Dr. Tomanes during his talk. And then next, we will actually look at a more example on how you can actually use Wolfram Notebook AI Assistant for your learning and teaching. Again, if you're not sure whether your organizations currently have Wolfram Access, you can also check. On the pop-up screen, there will be a survey that would direct you to Wolfram site info page. You can enter your institutional email address, and then it will tell you whether you currently have access to Wolfram. Next, I would like to invite Arban Kalziki, Wolfram certified instructors here at Wolfram Research, to share about notebook assistant use and applications for learning and teaching.
Today, I am quite excited to tell you about how to turn rough ideas into computation with Wolfram Notebook Assistant. Now, typically in our webinars, or at least in the ones I run, we'll have a bunch of pre-populated stuff in our notebook here, and I'll kind of, teach you about a topic. Here, I think it's better to just kind of see it in action and kind of learn through that seeing. I think at this point, we're all familiar with ChatGPT. And I would say that Notebook Assistant is like a custom version of ChatGPT that has access to all of our documentation and all of the data that makes, say, Wolfram Alpha so powerful. It knows, all of the functions in Wolfram language. And if you go to the documentation, you can see that there are over 6,300 as of the most recent release functions. That's quite a large number. It's nice to have a computational assistant for that. It knows about all the tutorials, all the examples. And like I said, it has access to all the data that powers Wolfram Alpha. It can improve your code. It can explain code that you got from somebody else. And as is the primary focus of this talk here, it can turn your rough ideas into computation. So Notebook Assistant, in summary, works like a hyper-smart, fully knowledgeable helper that lives right next to or inside of, you can open chat cells in a notebook just by typing an apostrophe. It just lives next to your notebook or inside your notebook. And if you want to use Notebook Assistant, you can sign up for Notebook Assistant and LLM Kit. And there's no configuration necessary. As soon as you kind of sign in to activate your product, it's all linked to your account and everything will just work. So let me show you some examples. We'll start kind of simple. Say I'm brand new to Wolfram language and I want to know how to do kind of a basic programming task. Let me say something like, let's say, how could I find the running maximum of a list? Actually bump the magnification here. It's a little bit small at 150 on this monitor. Maybe that's better for folks. And then I can just press enter. This gets sent to the assistant. And this gives us a nice little answer here. So in Wolfram language, we can use the fold list function. And here's an example of how this would work if we had some sort of list. And here, note that the function here is linked. So if I click this, this has actually opened up the documentation page so I can read all about this particular function that the assistant has linked. So here it gives us an example of this running. And then it also notes, and I think this is kind of a neat thing, that this has access to this through our documentation, that you can use this resource function that kind of automatically does the task that we've asked it to do. Resource functions kind of extend the functionality of Wolfram language. The way I always put it is, if you think 6,300 built-in symbols and functions isn't enough, if there's like some specific thing you find yourself doing really frequently, and you think maybe somebody else might like to use that, we have this thing called the function repository, where users and people from Wolfram here, we can all submit functions to the function repository, and then everybody can access them after they've been approved by us. And this will just grab the function right from the cloud, and we can just use it right in the notebook. Now, Notebook Assistant gives us this answer, and it gives us this code. And something that's quite useful is you'll notice that not only can we copy the code, we can insert and evaluate the code here. So if we click this, we get this, and we can see that indeed for this example list that it has come up with, at first, the largest element is 3, starts at 3, and then it stays at 3, and then 5, 7, and then once it hits 8, we stay at 8 because 8 is the largest entry. 7 isn't larger, 5 isn't larger. Once we hit 9, we stay at 9 because 9 is the largest entry. And there we go. So that kind of does what we'd like. Maybe we have an image in our notebook. So let's say we've got some cats. We'll just call it that. If you're new to Wolfram Notebooks, for reference, you can just copy and paste images right in here. You can also use the import function or drag and drop things from your file explorer. All of that stuff just works transparently. And once it's in the notebook, it's a fully computable object that you can do whatever you want with. It's really, really, really useful and nice for folks who do image analysis in particular, but it's also nice for, a hobbyist. And again, I've been in both of those positions. I've done some image analysis for things in a lab in grad school and just on my own. And I have a little example coming up to show you that. But now that I've got this cats here, I could say something like, how could I find where the cats are in the image cats? So here, it asks us to do this. And it tells us this is this function that could be used for this. This is actually, this is not something I was aware of. This is a new one. And so we go in here, it's giving us coordinates for where the cats are located in the image. There are a couple of different ways you could go about that. And, I'm going to ask and see if it's willing to suggest to us a different way, maybe. So two things to kind of notice here that I'm doing, again, a bit transparently. I ask, is there any other function that could do that? And it knows that I'm referring to this previous chat here and what we have in the notebook. So the Notebook Assistant is aware of the whole chat history above it, and it's aware of everything that's in the notebook over here that it's focusing on. And how can you choose which notebook to focus on? Right here, if you just click this, you can choose any notebook you have open. And you can also just have it choose automatically, which is the default. And what that will do is it will just focus on whichever the last notebook is that you've clicked on. So let me click this. Any other function that could do that? Yeah, so you could use image contents perhaps. And then here we get a nice little data set where it says, okay, we've looked in the image of that I've called cats here. There's nothing special about calling it cats. It's just what I've called it. And we're able to see, oh, okay, there's a domestic cat, and this is the little thumbnail, and another domestic cat, and this is the little thumbnail. And here are the rectangles that are the bounding boxes for these cats. And here are the confidences that this thing has, that this thing is a domestic cat in each case. So that's pretty nice, if you ask me. You can also ask kind of questions that are a little more, let's say, Wolfram-y in a way. Questions that take advantage of kind of the curated tower of knowledge on which Wolfram language rests. And you'll see what I mean by that when I ask, how could I make a 3D plot of the terrain around a mountain? Okay, so it's letting us know about these functions. Here's the thing. As an LLM-based thing, sometimes Notebook Assistant will hallucinate. I found it's actually quite good about not doing that. It really knows when to use Wolfram language and the Wolfram entity framework to get real hand-curated information rather than just crawling the web or using training data or using information that was in the training data. But even in the cases where it might hallucinate, you still get links to useful functions that you can check out. And so even if you can't quite get it to work, this is always a good starting place. But let's see if this did work. So let's just insert and evaluate this here. And that works, no question. So here we can see that we have used the geo-elevation data function here to get Mount Everest as kind of our center point. And then we're kind of looking at a 4-kilometer block around this. That's going to be our data. And then here, it has put that data into a list plot 3D. This is a function you can use to plot a list, which is a Wolfram language generalization of an array. And here, it just plugs it in, and it even cleverly, I do think this is actually quite clever, is it uses the mesh functions option and then specifies, this is kind of a pure function notation. It's like a lambda function if you're familiar with that. If you're not familiar about it, don't worry about it. It's not a big deal. You can always check the documentation if you're curious. But what this mesh function does is it's getting the third coordinate. That is, we think about the X, Y, and Z coordinates in a sense. It's getting the third coordinate and it's drawing nice mesh lines on there. And it's doing that because contextually it's aware that if you kind of want to look at elevation data, you often want to have these lines that indicate how high up you are, these lines of constant elevation. And that can give you a sense of how rapidly the topography is changing. So here we see it's very steep. We see a bunch of lines gathered together, whereas here the topography isn't changing too much. The elevation is pretty constant, so we don't see too many contours there in a sense. And now, because the Notebook Assistant is aware of the previous conversation and of what's in the notebook, I can say things like, oh, that's great. People go back and forth on this, but I have tended to notice that when you're dealing with an LLM, being polite does get you generally slightly better results. This might sound a little bit kooky, But if you think about the way LLMs are trained, right, they're trained on a bunch of training data. And generally in the training data, when you have somebody kind of politely asking a question or having a conversation, the responses to somebody being polite are going to tend to be a little bit better. So let's say, oh, that's great. Could you make it so the color of the plot depends on the height? Okay, so it gives us some new code here. And if we just insert and evaluate this, we get indeed exactly what we wanted. We can see that we've got a rainbow color scheme here that was just kind of the default that was picked for this. You can ask for other color schemes if you know about them, or if you kind of want to just get roughly close to like an idea of a color scheme you have. But there we go. We're able to pull in this geographic information through the geo-elevation data function. And we're able to pull in all this surrounding information about, what is Mount Everest? Where does it exist exactly? What are its geo-coordinates? All that stuff just happens transparently in Wolfram language. And then it's even easier here because you don't even have to have known about this stuff. You can then just ask Notebook Assistant, and not only does it do it for you, but because it provides the code, you can look and you can start to get a sense of like, oh, this is pretty neat. I bet if I put in, another mountain here, let's say, is that right? Is that how we think about that? Then I could run this again. And here it is for K2, different mountain. It's actually quite interesting the way that looks there. Maybe if we have any volcanologists in the audience, they know exactly why it looks like that. But to me, a layperson with respect to mountains, which is not a sentence I find myself saying frequently, I think that's quite interesting topographically. So that's just kind of a little example of being able to write code that pulls in functions that use real curated data that we have access to through Wolfram language. You can maybe take a step back and do something maybe a little simpler in a sense. Maybe you were working with some graphs, not graphs in the sense of like the plots of a function, but graphs in the sense of like a network. So maybe I have a graph and I want to swap the nodes and edges. I can just ask about it. Okay, so it suggests using the line graph function, and then it comes up with some example code. So suppose we have this original graph, we can then swap the nodes and edges by using this. And if we click on here, let's go ahead and not suppress. A semicolon suppresses output. So we're going to leave the original output of the original graph. We're going to see that this is the original graph, and this is the graph with the nodes and edges swapped. So now not only do we get a result, but again, we can see an explanation for what the code is doing, and we get to learn about the function line graph. And again, if we click that, it pulls the documentation right up. And again, for folks who are newer to Wolfram language in particular, there is something I want to note about the documentation. Well, a couple things really. One, the documentation is really good. We spent a lot of time making sure that it's very thorough, has a lot of useful examples and details, even things like neat examples. But maybe more relevant to the Notebook Assistant is maybe it gives you a function and it's really close to what you're asking for, and you can't quite figure out how to ask for exactly what you want. What you should do is you should just click on that function name, come to the documentation here, and look at See Also. And in many cases, if the function that was suggested isn't quite the one you want, you'll be able to find the one you want and See Also here. So you could click in here and say, oh, okay. Well, this is what I wanted. I actually wanted to get the graph complement here, which does this. And then you can look at all the examples, and maybe this one isn't quite what you want. Maybe you say, oh, I wanted the graph intersection or something like that. And it's all just there in the documentation. And if you have any questions about anything in the documentation, guess what? You can ask Notebook Assistant about it. we can do things like, suppose that I've got a CSV file and I need to make a plot. Well, that's a very common use case in my experience. So it might be something where, again, if you're new, you might not know how to do it. So you could say, how could I make a plot from a CSV file? Okay, so it gives us kind of all the steps. We should use the import function to read the data from the file, and then use a plotting function like listplot or datelistplot. Importantly, not just the plot function, which plots functions rather than data, but listplot and datelistplot, which are what we want for a CSV. We can use those, and there we go. And here it gives us, how do we import something? And then it says, here's how you would plot it.
Thank you very much, Arben, for sharing some more examples for a Notebook Assistant. So shifting gear a bit, I would like to introduce you to our next speaker, Associate Professor Febdian Rusidi, who is the head of Research Center for Quantum Engineering Design at Universitas Erlangga in Indonesia. He has kindly able to join us today. So if you have any questions, if you're interested in this particular area, you can use the chat environment to post your questions for Professor Febdian Rusidi. So yep.
This recording is my talk on my first-hand experience utilizing Wolfram Mathematica in the exploration of instructional concepts for molecular physics. By instruction concept, I meant a general guideline on how I use Wolfram Mathematica to design my teaching and research workflow. The message that I want to convey to the audience, according to my 18 years of experience in teaching and research, is that visualization is not just plotting. It is the essence of understanding, at least in my field, molecular physics. I genuinely appreciate your time and effort in attending this seminar. Therefore, I will share the conclusion of my presentation immediately. This way, you can decide whether to pay attention to my talk or better to take a break and come back in Q&A session. And here is the conclusion. Wolfram Mathematica plays a crucial role in helping me prioritize physics in teaching and research that require computations, tabulations, and visualizations by assisting me to concentrate on the content rather than the detail of coding and programming. Therefore, I have more time to explore ideas and other possibilities. My name is Febdian Rusdi. My affiliation is Research Center for Quantum Engineering Design, Faculty of Science and Technology, Universitas Airlangga, Surabaya, Indonesia. I divide my talk into 3 sections. First, I begin with waves, where we will see the importance of mathematics in physics. Then, I continue with the hydrogen atom, where we will see the importance of visualization in physics. Finally, I believe the most fascinating aspect of my talk, thought I will keep it short due to time constraints, is the integration of Wolfram Mathematica into our research in the field of molecular physics, which I call neo-conservative approach. Of course, I will try to make as brief as possible for each section. However, if you find me take times at certain explanation, you may go, but please do not go away. Let us begin with waves. Why waves? That is because molecular physics must be understood in the framework of quantum mechanics. And in quantum mechanics, we treat particles using the wave equation of motions to reveal their wave-like properties. Electrons are particles. They have wave properties. We use the wave equations for particles, and the solutions to the wave equations are wave functions. waves than the central concepts in molecular physics. That is why we must begin with waves. Look at these four mathematical functions. We have trigonometrical functions sine x, cosines t, sine x plus t, and cosines x times t squared. Function A, B, C, and D. Surely, everyone knows only C is wave. But does everyone know why D is not? Function A and B are visualized by plot, while function C and D, because of time variable t, visualized by animated plot. Where wave is always in motion, therefore, an animated plot is the correct visualization. This is only a small example of how important mathematics is in physics. Without mathematics, we cannot visualize. If we cannot visualize, it is not physics. Wolfram Mathematica provides precise functions that enable accurate visualization of physics. So, Wolfram Mathematica provides precise functions that enable accurate visualization of physics. In our case, the function animate plot is responsible for visualizing wave functions, while the function plot is for visualizing a portrait of wave function. Both are important in quantum mechanics. But what is the portrait of wave function? Like portrait of ocean wave, it appears at rest, but we know that they are always moving, as shown in the following examples. Wolfram Mathematica can search and display images without us stealing it from the internet. Why the function D cannot describe a wave? The reason is that the variables in physics needs units, such as time variable has unit second, position has meter, and mass has kilogram. That's why people said physics is mathematics with unit. Unfortunately, not all mathematical functions can operate on units. For examples, trigonometric functions work only with degree or radians, and they do not work with others unit. Wolfram Mathematica, we can see here, not only does symbolic computation, but also manages the unit of variables. The wave function is based on the function c, sine x plus t, but the variables x, t are position, meters, and time, seconds. To make it work, the variables must be in the form of ax, bt, where the vector a, b must have unit radians per meter and second per meters. Both radians per meter and second per meters are physical quantities, as we can verify using the provided free form unit of inputs. Wolfram provides valuable information, but the most relevant one for our context is this, physical quantity. We found out that radians per meter is angular wave number, and radians per second is angular frequency. Both are physical quantities related to waves. However, the function d, sine x t squared, requires a vector with unit 1 per second square meter. After we check the unit with the free-form input, we find out it is not physical quantity related to waves. That is the reason why function d cannot represent waves. We learn here that the free-form input most of the time helps us to utilize Wolfram Mathematica without worry with built-in functions. Before we continue, let us wrap that we have done so far. We introduced two fundamental concepts to teach physics interesting, attractive, and more importantly, elegant. One, a computational on-fly method to see the concept of physics. 2. Assessing curated scientific and technical formulas to improve study efficiency. Recommendation: stick to one Wolfram Mathematica built-in function at a time, no nested operations. That's how we keep frustration away from students. Now we discuss the second topic, the hydrogen atom. The hydrogen atom consists of one proton and one electron. These two particles have wave-like properties, so we must study them using quantum mechanics. Quantum mechanics is based on quantum theory. Quantum theory is as simple as this. If it were a particle, study it using the wave equation of motion and vice versa. One of the wave equations for particles is the infamous Schrödinger equation. It is infamous not only because of how Erwin Schrödinger came up with this equation, but also because the equation already failed many students in exam. The equation has position dimension and also time dimension. It is wave equation because the solutions are wave functions, similar to what we have discussed in the previous section. It is for particle because it has mass and only particles have mass. If the solutions do not change shape over time, we call these solutions stationary states. For the stationary states, the equation is reduced into the position dimension only, or time independent Schrödinger equation, and the solutions become the portrait of wave function, CR. Now, let us go back to the hydrogen atom, where we have one proton and one electron. In other words, hydrogen atom is a two-body system. It is impossible to have a complete solution of two-body system unless we introduce some approximations to reduce the two-body into one electron system. The approximations give us the time-independent Schrödinger equation as follows. There is no mass in this equation, and potential is Coulomb interaction only. It means the equation ignores proton and considers the electron is at rest. Of course, these two assumptions are not correct. In fact, it is the biggest flaw of the model. However, it turned out of this biggest flaw produced the perfect results. Since it is quantum mechanics, the question why it is like that is invalid. As long as it works, we remain silent and continue using it. Wolfram Mathematica offers many ways to solve the hydrogen-like time-independent Schrödinger equation. The conventional one is to use the function of the solved family. But we are physicists. We don't have time for solving mathematical equations. And Wolfram Mathematica lets lazy scientists like us study physics without worrying too much about mathematics. A better way is to use the function Schrödinger PDE component. PDE stands for the partial differential equation, which is the left side of the time-independent Schrödinger equation. This function is so flexible for quantum mechanics problem. Since hydrogen atom is only a very teeny part of quantum mechanics problems, some nice and charming people already make add-on function for the solution of hydrogen atom. The function is stored in Wolfram repository system and can be called as follows. The syntax contains quantum numbers n, l, m, Bohr radius a, spherical coordinates r, theta, phi, and nuclear charge z, which is equal to 1 for hydrogen atom. And here is some example for 1, 0, 0. Then 2, 0, 0. And 2, 1, minus 1, 2, 1, 0, and 2, 1, plus 1. Very fast, very simple. Besides Wolfram Mathematica, there are a lot of tools out there, free or paid, that provide the computational solutions for the Schrödinger equation. including for hydrogen atom. But students still hate the Schrödinger equation. Why? Because they do not understand it, even though they may be able to get the solutions and plot them. Look at this example. This is for 300, 310, and 320 solutions. And we can plot it right away using plot. This is the result. But again, even if we get the result, we still don't know what it is. Why we cannot understand? So we hate it because we do not visualize them correctly. The correct visualization requires statistic understanding. Quantum wave functions do not hold any physical meaning except for their square of magnitude. The square of magnitude of psi is probability density function, or PDF, which tell us the probability to get a certain value. For example, the most common PDF is the normal distribution. We can get the mathematical expression and all necessary statistical properties of the normal distribution as follows, which is colored in red. Wolfram Mathematica offers a way to explore the PDF on the fly using function manipulate like this. We can play around with the values of mean and standard deviation. In my opinion, manipulate is the most powerful function to explore physics. I learned this function from my brother Ruben Garcia. I remember clearly when he taught me this function in 2019, he said manipulate instead of manipulate. I keep saying the same name, manipulate, to show my gratitude to my teacher. Ruben, thank you very much. In our case, the solution NLM are commonly refers to orbitals. The orbital have names. Here is for examples. The square of orbitals is a PDF, which provide us with the probability of finding electron at specific positions. For examples, here is the density of electrons in 2s orbital. Electrons will be here, but we will not find electrons in this area. If we want to explore more, we can plot them under the function manipulate as follows. This is for 3s, so we will not find any electrons in this area and also in that area. If we go to 4s, we will also not find electrons in this area, and so on. Visualizing orbitals using this way helps instructors to spend time more on physics than on mathematics. Based on this idea, I have written 2 books where I use Wolfram Mathematica to teach by exploring the equations. One book is already published and have been used in my class entitled Atomic and Molecular Physics in the Framework of Density Functional Theory. And another one is in the production house of Airlangga University Press entitled Quantum Mechanics Exposition in Molecular Physics. In the second book, in this book, I even put chapters and sections to explain how to use Wolfram function. Here I explain about the Wolfram Mathematica and also Gaussian 16. And especially in appendix, I put how to use function Wolfram Mathematica, how to convert the units, also how to visualize data using Wolfram Mathematica. And this is example how I explain to the readers using Wolfram Mathematica. So what we have done so far, in addition to the first 2, we got another 2 concepts. We already demonstrated the importance of visualization to understand physics concepts, emphasizing the essence of teaching, visualization, and good narration, establishing a cleaner and clearer way of teaching with Wolfram Mathematica to achieve the essence of teaching. Recommendation to avoid coding here. Our intention is to explore physics, not making a nice script. Finally, we come to the last section of my talk, which is the most amazing one. We use Gaussian software in our research, and it helps us a lot. However, since I integrated Wolfram Mathematica in my research practice, my productivity is increased exponentially, as shown in this illustration. Now, I have time to write books and modules for teaching, as I have shown in the previous section, something that I cannot do it before. Of course, I do not do any coding with Wolfram language. I only take advantage of the Wolfram Mathematica capabilities, such as the function of manipulate, add-on functions, Wolfram repository, and more. Research practice is presented in a research workflow. My conventional workflow is as follows. I did the preparation, drawing molecules, and post-calculation works, tabulations, and visualizations with various software. Now, with Wolfram Mathematica, instead of draw the molecules, I curate them from the Wolfram repository, then tabulate and visualize the result using one software, Wolfram Mathematica. By doing so, it is not a surprise that I still have extra time to do some exploration. I call the new workflow as neo-conventional approach because I am not confident enough to call it a new or modern approach. Not to mention, neo is a cool term. It reminds me of the Matrix movie. Here is our current study, the structure of curcumin. We have been studying how to increase curcumin solubility in water. One of my students, Caca Royhatul Madinah, took these subjects for her master research and got some finding. She published the finding already, as shown in here, web search. The study is far from complete, but one thing for sure, we always need the precise structure of curcumin. Instead of drawing, we curated the molecule using the function molecule. The good thing about this curated structure is that it was based on the experimental results. The advantage to use the curated data is that it speeds up the optimization process by Gaussian 16. I label the structure from curated data with kunyit. I learned a wisdom here. It is better to use Bahasa Indonesia for labeling. Why? I can use various names without worrying about conflicts with built-in names in Wolfram that typically use English. Anyway, we can display the molecules in 2D and 3D graphs. The 3D display can be rotated. The most important steps here is to save atoms coordinate from the curated data. We can use function export to save the data and check it using function import. Here we have the atoms coordinates that can be used in the Gaussian input files. Gaussian saved its calculations results in a log file. Wolfram Mathematica can read Gaussian log file using the function import. Here, kunyit log is the label for the log file. The information contained in the log file can be revealed using meta information option. We have the header, which tell us the software and the exact commands we use for the calculation. Then we have physical quantities, such as the dipole moment, the orbital energies and occupancies, rotational constants and symmetry, the vibrational frequencies and intensities, and the movement of atoms during vibration. The array means Wolfram Mathematica already tabulated the result, which means we can manipulate them and visualize them as need. We start with the most crucial quantity, which is the collective effect of all classical and quantum phenomena experienced by electrons within a molecule, the electric dipole moment. This is how we extract the information from the log file. It is a vector quantity. That is why we have three values, x, y, and z component. Each values has the unit of dB. If we do not familiar with one unit, we can convert it into SI or SI base unit, like the following example. Here, we use SI base to convert unit dBs to unit of meter second amperes. We can also display the dipole moment of the molecules as follows. We also can rotate the molecule. Most of chemical properties of molecules determined by frontiers molecular orbitals. Two most important frontier molecular orbitals are the highest occupied and the lowest unoccupied molecular orbitals of HOMO and LUMO. The identity of these orbitals are the numbers of electrons occupied the orbitals and the energy. We label them with Hunian and energy. To open up the array, we can use the function normal. For example, here is normal Hunian. LUMO. LUMO is the first orbital with zero occupancy. Therefore, we use the function first position to get Hunian 0. We got the result 98, which means MO number 98 is LUMO. It is somewhere in here. This is LUMO. HOMO is one orbital right before LUMO. So we only need to subtract LUMO with 1. The energy difference, or some people call it band gap, is easily calculated using this method. We label it with celah, and it has magnitude and the unit of energy in Hartree. One of band gap analysis, in particular in photochemistry, is to determine the light's wavelength to excite the molecule. This can be achieved by following procedure. First, we find out the formula using the function formula data and substitute the band gap energy into the formula. Here is the light's wavelength to excite curcumin. Time is up, and this is my last page of talk. It is perhaps the ability that newbie in molecular physics like to use, visualizations of orbitals. Log file does not have this information. Therefore, we must run additional Gaussian 16 job to create cube file for HOMO and LUMO. Once we have the cube files, we can display them using the function import as follows. There are so many can be done, such as bond analysis, but again, I am a guest here and must obey the 25-minute rule. Thank you for your kindness attention.
Thank you very much, Professor Fabdian Rusidi, for sharing about your projects. If you have any questions, feel free to pop it on the chat on the right hand side, or you can also share it via email, and then we can share your questions with Professor Fabdian Rusidi. Before we move on to our last talk of the day, I would just to remind you at the end of the event, you'll be prompted to answer a survey. And if you would like to receive your certificate, your attendance, don't forget to tick yes as well, so our team can send that as well to you after the event. For the last talk, this will be by our applications engineers from Wolfram Math Core teams on Wolfram System Modeler, and the use in solar rooftops to power grids, and it will be on modeling energy systems.
Hello, everyone, and welcome to this talk titled From Solar Rooftops to Power Grids. I'm Ankit, an applications engineer from the Wolfram System Modeler team. In this session, I'll walk you through a use case that highlights why simulation is essential in driving the energy transition, from understanding household behavior to designing resilient power systems. The world is electrifying and the pace is accelerating rapidly. In the next 6 years, global electricity demand is expected to rise by around 6,500 terawatt hours, according to the International Energy Agency. To put that into perspective, that's like adding another United States worth of electricity demand. And the US is already the second largest consumer of electricity after China. This surge is driven by data centers, the electrification of heavy industries, electric transport, and other emerging sectors. But while global demand keeps growing, let's take a moment to look closer to home and see what the current reality looks like. For this presentation, let's focus on South Africa, a country that reflects the situation in many developing economies around the world. It has a growing economy and a young population, especially when compared to developed nations. However, since 2018, South Africa has experienced frequent load shedding, largely due to aging power infrastructure and insufficient generation capacity. While the situation has improved somewhat in 2025, load shedding remains a daily reality for many households. What's more concerning is that costs are rising too. Compared to 2003, the residential electricity tariff has increased sixfold. So, while people are paying more for electricity, they're actually getting less reliability. In short, bills are going up while the lights are still going out. Unreliability isn't just a theoretical concept, it has real, everyday consequences. Your fridge warms up and the food inside spoils. Your lights go out in the middle of an important task, maybe even a job interview. Or your washing machine stops halfway, wasting both time and energy. So, how do we move towards a more reliable power supply, one that's built on informed technical decisions without spending a fortune on oversized systems? Let's explore our use case through a household in Johannesburg. Before we look for solutions to improve reliability, it's important to first understand the electricity demand and identify the main contributors. Climate plays a big role here, influencing seasonal heating and cooling needs. So, let's start by gathering data for Johannesburg. Using the Wolfram language, we can easily connect to open data sources like PVGIS to extract solar radiation and temperature information for the region. Once we have this data, we can build a generic household energy model based on engineering first principles to estimate electricity demand from different sources. Now, before diving into the details of that model, let's look at what the simulation results tells us. For a 100 square meter house, the model predicts an average consumption of around 650 kilowatt hours per month, which stays fairly consistent throughout the year. The major contributors to this demand are electrical appliances, followed by water heating and space cooling. During the winter months in South Africa, roughly May to August, the demand shifts towards space heating, while the rest of the year is dominated by cooling loads. As you can see from NREL data, the electrical load, which includes lighting, cooking, refrigeration, and television use, makes up the largest proportion of household energy demand for a middle income group. This is followed by water heating and then by space heating and cooling. Now let's look at one of the submodels I use to predict space heating and cooling demand. This is a house model built in Wolfram System Modeler. Here, the thermal inertia of the building is represented using a heat capacitor component. Here, multiple heat sources and sinks are connected to it through input signals such as solar radiation, ambient temperature, and heat losses to the surroundings. We also have a controller in the model that maintains the indoor temperature. It automatically switches on the radiator when it's cold or activates the air conditioner when it's hot. In addition, there is a component that accounts for heat generated by occupants inside the house. The plot you see here shows the simulated results across 10 different years, capturing how the building responds to changing seasonal conditions. I won't go into all the other submodels now, but if you're interested, you can find more details in the link provided here. To summarize, what we have seen so far is a simulated model of a household in Johannesburg, capable of predicting energy demand based on different heat loads and climate factors. Next, let's look a bit deeper into the resulting demand profile over a span of a few days to understand how load fluctuations occur in practice. If we dig a bit deeper into our household model, we can start to observe some sharp transitions in the energy demand as shown in this plot. A lot of data contributes to these variations: heating or cooling based on temperature, lighting that switches on and off depending on solar radiation levels, and other appliance usage patterns. Still, we can identify some general trends. After midnight, the demand is mostly from heating and cooling loads. During the day and early afternoon, when there is sunlight, fewer people at home, the demand drops to a low level. Then, in the evening, we see a few distinct peaks caused by activities such as cooking, using the dishwasher, or watching television. This profile represents a typical residential load. Now, if we shift perspective and look how an energy provider views the same situation, aggregating data from homes, offices, industries, and other facilities, we see a different pattern. Such a plot usually shows two main peaks: one in the afternoon when the offices are running at full capacity, and another at night when households become active again. My current model focuses only on residential consumption, so it does not include the daytime commercial peak, but the overall trend remains similar across most regions. So far we have looked at the demand side through simulation. Now let's turn to the grid side and understand what happens when demand and supply fall out of balance. When you talk about the grid, you often hear terms like frequency and voltage. Let's use a simple model to understand why load shedding occurs. One of the main reasons is that demand exceeds supply, and as a result, the grid can no longer maintain a constant frequency. Imagine a gas turbine generator with a rotating shaft. The rotational speed of this shaft determines the frequency of the AC power it produces. In normal operation, the turbine rotates at constant speed, generating electricity at around 50 Hz. As the demand increases, the controller tries to supply more power by increasing torque. Initially, the rotational speed stays stable and the frequency remains close to 50 Hz, with only minor fluctuations as the controller adjusts. But as the load continues to rise, the turbine eventually reaches its maximum deliverable power. Beyond that point, it can't increase torque further, so it starts losing rotational speed. This causes the grid frequency to drop below 50 Hz. A falling frequency can quickly affect all connected equipment, from household appliances to industrial machineries. And to prevent that, the grid operator must shed some of the load, which is what we experience as load shedding. Now that we've understood how demand dynamics and grid stability interact, let's look at what we can do at home to manage our own power usage and even help make the grid more resilient. Let's start by adding a battery to our household model. In the same diagram that I used earlier for the grid, I have now extended it by including an electrical battery system. All the components you see in this system model diagram are built using free open libraries that are supported by Wolfram System Modeler. Once the setup is ready, I can easily experiment with different battery types and capacities, and then simulate how the system performs. In this example, I began with a 10 kilowatt hour battery, which roughly matches the daily requirement of this household. And to make the concept clearer, I simulated a simplified scenario where the grid supply is limited to 800 watts, while the household peaks at around 1 kilowatt during the evening hours, roughly between 5 to 9 pm. In a traditional setup, this shortfall would cause a power outage or load shedding. But in this model, the battery compensates by supplying the total energy during that time window. So from this simulation, I can also calculate how much stored energy is needed to cover an entire blackout period. In this case, about 10 kilowatt hours. This kind of model can be used to explore strategies like peak saving, where you use stored energy during expensive tariff hours to reduce electricity costs. The advantage of simulation is that it lets you design and test different storage configurations before making any real investment. Now, let's move to the next step by adding rooftop solar to our system. Now, let's add a rooftop solar to our model and make the household operate independently of the grid. In this version, I have replaced the grid connection with a solar power model, which can be parameterized using real design data from commercially available solar modules. Once the setup is complete, I can simulate the system to see how it performs and whether the sizing of the solar array and battery is appropriate for my household's needs. In this plot, the blue curve shows the solar power generation throughout the day. You can see that during the afternoon, when the sunlight is abundant, the solar energy is used to meet household demand and to charge the battery. The subplot below shows the state of charge of the battery. It increases towards 1 during the day as the battery charges and then gradually discharges in the evening, reaching a minimum of around zero point 0.5 by night. With a model like this, I can now answer practical questions such as what type of solar panels are best suited for my home, what battery capacity should I choose to ensure reliability. By simulating these scenarios first, I can make data driven design decisions before spending money on hardware. This type of model is not limited to a single residential building. It can easily be scaled up to represent entire communities by adding multiple demand centers. In such a setup, the households can share energy resources, distribute their storage costs, and have solar panels spread across the community, making the system more cost effective and resilient. In the simulation shown here, you can see that after around 9 pm, the battery is no longer able to deliver the required power. The state of charge drops to zero, indicating that the battery capacity is insufficient. So, in this case, we would need to choose a larger battery. This demonstrates the true advantage of simulation. You can make a model, you can reparameterize it easily, add new components, scale up the system, and study different load patterns or configurations. You can also include realistic data such as temperature, solar radiation, and household demand to test a wide range of operating conditions. Beyond that, you can even simulate fault scenarios, for example, during maintenance periods or unexpected outages, to answer practical questions like how much backup power is needed to meet the demand, what happens if one subsystem goes offline. And by doing this virtually, we make well informed, low risk decisions about how to design and manage reliable energy systems, from individual homes to entire neighborhoods. To summarize what we have explored in this presentation, we saw how load shedding disrupts daily life and how simulation helps us understand and solve this challenge step by step. We used models to study household energy demand, simulate batteries to find the right size, and integrate PV systems to achieve greater reliability even during blackouts. We then extended the same approach to community scale systems, showing how one model can be reused and scaled to design grid independent neighborhoods. In short, we saw how simulation makes scenario testing easy, helping us make smart, data driven energy decisions before making real investments. In this presentation, we moved from grid dependence to grid independence and ultimately to the idea of grid support, where households not only consume power but also contributes to grid stability. Simulation empowers us to make smarter design decisions and helps us make the right energy choices for our homes and communities. Thank you.
Thank you for sharing about system modeler, Ankit. So we have come to the very end of our session for today. Thanks again, everyone, for joining today, and to our speakers who have generously shared their expertise